Okay, thanks, Gunther, and thanks very much to the organizers for having me here and for the invitation to speak. I'd like to. So I'm going to talk about fusion systems with Benson-Solomon components. So it's an involution centralizer problem for some exotic two fusion systems. So I want to start at, and it's joint with Ellen Henke. I want to start at the beginning in the 1954 ICM address of Brouwer, who lamented the state of finite group theory and said that he was going to, well, I'm paraphrasing, he was going to reinvigorate it. And I guess that's what he did. He presented the Brouwer-Fowler theorem, which said that finite simple group is determined up to a finitely many possibilities by the structure of a centralizer of an element of order 2. And he presented maybe the first involution centralizer problem, so maybe too simple, where he considered an involution centralizer GL2Q. So Q is always going to be odd. And he showed that G must be PSL3Q or M11 when Q is equal to 3. Okay. So it seems like a good thing to do, and I guess the next person I think to take up such a problem, as far as I know, was maybe the early 60s, Thomson, who considered involution centralizer isomorphic to cyclic 2 cross PSL2Q, and with the group has abelian CeLO2 subgroup. And he showed that the recently discovered regroups were the only examples for Q greater than 3. On the other hand, Henke was working on the problem independently about this time, and he, I guess, was in touch with Thomson and was considering the same problem, and he could reproduce Thomson's results when Q was bigger than 5, but Q equal to 5 was a sticking point. So Henke actually shows that it's not the case. You have for Q equal to 5, you have a new sporadic group. Not so let's fast forward to say 1972, when Lynd considers the double cover of A11 as an involution centralizer, produces the Lynd group.
Justin,
Yeah.
you want to say 2G2 or do you want to say 2G?
2G2.
And also, probably you want to mention that John Thomson did Bomberi help, right?
Yes. Oh, who did?
Enrico Bomberi.
Ah,
Yes.
I'm not aware of that. So there's a paper
I
by.
didn't find the book, yeah.
There's a paper. Oh, you mean in the construction of the regroup?
Well, to show that this is a unique one.
Oh, okay. Yes. I see. Yeah. Right. Yeah. So, okay. So that was. So Lynd's found something, and this was the environment when in 1974 Solomon considered an involution centralizer, a double cover of an orthogonal group, 7-dimensional orthogonal group over a field of odd order, and found, well, eventually a contradiction, because he could show the CeLO2 subgroup of a hypothetical simple group was that of spin 7 of Q itself, and knew the pattern of conjugacy of two subgroups in that CeLO2 subgroup, but upon switching to the prime which Q is a power, he obtained a contradiction. But in hindsight, Solomon had discovered was not a finite simple group, but an infinite family of exotic two fusion systems. The Benson-Solomon system. So this is 28 years. Rather than all of it. Okay, so that's what this talk is about, and basically the whole point of the talk is to fill in, I'm going to take a quite leisurely pace, but I want to fill in a line where we look at involution centralizer for the Benson-Solomon systems themselves, and fill in the blank. Okay. So I should probably tell you what a fusion system is. So that was the sort of the intro. And so now let's define a fusion system. Always have a finite group G, a prime P, and a CeLO P subgroup of G. And then you can make a category. Where the objects are so this is a category. The objects are the subgroups of S, and morphisms are a set of group homomorphisms from P to Q, which are of the form conjugation by G, little g. Whenever G, little g conjugates P into Q. Okay, so this is the fusion system of G. And we want to abstract away the group. So let's see. Okay. Yes. So now we'll try to abstract the group out of the picture. So and define what's called a saturated fusion system. So that's again a category. The objects are again the subgroups of S. Morphisms are denoted by Hom sub F P Q. They are required to be injective group homomorphisms, and they're required to contain the homomorphisms induced by conjugation by elements of S. So that's the minimum requirement. There's one more axiom. It's a very weak axiom, but I don't think it does good to, I just won't say it. And this gives you what's called a fusion system. So fusion system on S. And then there are two more, to get a saturated fusion system, there are two more saturation axioms, so-called saturation axioms. And one says that, so maybe this one's called the CeLO axiom. And it says that the group of inner automorphisms of S, which is, in other words, aught S of S, and whenever I write aught sub something, we're working with categories where every self morphism is an isomorphism, so that's just on S. So that's a silo, that should be a silo P subgroup of the full group of F automorphisms, the full group of F automorphisms of S. And then there's one more axiom called the extension axiom. Which I won't give, but if you verify, if you go about verifying it in the standard example, what you'll use is, well, this is silo axiom enforces Silo's theorem in an obvious way, but extension axiom also, yeah, so when you verify extension axiom in the standard example, you'll be applying Silo subgroups and normalizers and centralizers of P subgroups. So it really is another Silo axiom. So more generally, so this, so this is a saturated, so category satisfying all these saturated system. Yeah. So more generally, if you have a block B of a finite group algebra and characteristic P, then you can make a saturated fusion system over what's called the defect group of the block. I think that's known to people. If you take the principal block containing the trivial module, then you get the fusion system of the group. Okay, so we say that a saturated fusion system is exotic if it's not of the form if it's not of the form Fs of G for any finite finite G. And S zero tend to be. Okay, so so when P is odd, there seem to be. I mean, we heard about fusion systems over on P groups with P odd last Tuesday. So there, the general pictures of there are lots and lots of them, and people, including probably some in this room, are cataloging them. So at the prime 2, we only know the exotic fusion systems at the prime 2 that came out of Solomon's problem. And of course, you know, things you can build from that in an obvious way. So, actually, it's they seem to be parametrized by prime powers, but two Benson-Solomon systems are isomorphic in a sense which can be made precise if and only if the two part of, so for Q and Q prime, if and only if the two part of Q squared minus 1, Q prime squared minus 1 are equal. So in fact they form an ascending chain. So let's see. Form an ascending chain. Sol 3 at the bottom. Sol 3 squared, so on. And actually, there's an infinite object. In fact, in a sense, which can be made precise. Also, a fusion system in some sense, but there's a space called DI4, which is discovered by Dwyer and Wilkerson in 1993, which is in some sense it's a homotopy loop group at the prime 2. It's so-called a 2 compact group. And okay, so if you look at its classifying space, classifying space has certain self-maps, called Adams operations, which four has certain self-maps. And Benson took, by taking homotopy fixed points under this map, Benson constructs and spaces which should be thought of as the classifying spaces of the Solomon fusion systems before the fusion systems themselves were around. There were no objects, but I think Dave was very instrumental in pushing that there should be some objects behind it. Right. Oh, I was going to say, yes, if you look at the size of the CeLO 2 subgroups here, another thing I should probably say is that if I write, sometimes I'll write G, that's probably not a good thing, but yeah, sometimes I'll just put maybe write F sub 2 if I don't want to specify the CeLO 2 subgroup, and Conway 3 at the prime 2 is contained in the smallest one. That was and that was supported by cohomology calculations by Benson and verified by I think Aschbacher and Sherman at first. But anyway, okay. What's next? Yes. Oh, yes. I was going to say the size of the CeLO 2 subgroup here is order 2 to the 10. So this is on a 2 group of order 2 to the 10, 2 to the 13, 2 to the 16, and so on. This is relevant because the recent result of Anderson, Oliver, Ventura shows that there are no exotic fusion systems, saturated 2 fusion systems over or on 2 groups S with order at most 2 to the 9. So in some sense, this is the one of the smallest. That's the only one we know. Okay. Right, so I thought I think I have time to sketch how one constructs a Benson-Solomon system. So I'm going to try to do that. So this was the 2 different constructions. One by Levy and Oliver, I think, is the one that I'm going to sketch. But it's so let's take let's let H be a 7-dimensional. So HB spin 7. So it's a double cover of the simple 7-dimensional orthogonal group, and has center of order 2. Let's call it generator Z. it's a fact that if span 7 has two conjugacy classes of involutions, one consisting of Z and one all the non-central involutions. And so if you take an element and so if you take an element, an involution which is not Z. Yeah. So its image will have a four-dimensional minus. It'll be an involution, and it'll have a four-dimensional -1 eigenstrace. So general fact that in an orthogonal group, involution pulls back to an involution in spin if and only if the dimension of the -1 eigenspace is divisible by 4. Okay, so let's let U be the 4 group generated by Z and U, and look at its centralizer in H. Right, the centralizer, of course, was going to respect the eigenspaces, so it'll have a big normal subgroup, isomorphic to spin 4Q, spin plus 4 of Q, a commuting product, spin 3 of Q. In fact, it's of index 2 in this. This has root system D2. I mean, there are a number of ways to say this, but it says root system D2, which is A1, A1. It says root system B1, which is also A1. So what we're actually looking at here is a commuting product of SL2Qs. And it has center of order 4 and center U. So you can already see there's a little bit more symmetry here than what's suggested by the geometry or than what's suggested by the geometry. So this is a commuting product. It's not simply connected, but it's a fundamental group of order 2. You mod out by minus I, minus I, minus I. And you get that group. Now, I guess we're after, let's see, what is the full centralizer in H of U? That's L1, so let me just schematically draw it. So it's this commuting product for SL2Qs extended by a diagonal automorphism of order 2 that normalizes each one of them. And then the normalizer in H of U is L2, L3, extended by a 4 group in which W swaps the first 2 and centralizes L3. So we're interested in the 2 local structure. So let's fix Silo 2 subgroups of these SL2Qs. And these are quaternion, and so if we look at the 2 group that we get, this is a Silo 2 subgroup of H, and the centralizer, and the centralizer in S of U is what you. The product of these quaternion groups extended by this this involution. Okay, so so the theorem is, which is shown, so the theorem of Levy and Oliver in a roundabout way, I guess, also Aschbacher Chermak, that there's a is an essentially unique automorphism gamma such that gamma generates with the fusion conjugacy already present in 7, a saturated fusion system. And so the key word here is saturated, because probably the automorphism of order 3 that you're thinking of right now is not the right one. At least when Q is not congruent to 3 or 5 mod 8. I mean, so this is a delicate thing.
You didn't say gamma had order 3. You meant
Order 3, yeah. Thanks. And that's how you get a Benson-Solomon system. So let me just mention some facts. F equals 3, 2, 1. It's simple. In a sense, I won't really define it, but at least pay lip service to it later. It's simple. Its Schur multiplier is trivial, and its outer automorphism group is cyclic of order 2 to the L. Generated by field automorphism. So this the first two are due to Winkleman, and Alan and I worked out the outer automorphism group because we needed it. Now, if F were the fusion system of a block, then, well, it's not. Let's do it, Kessler and Craven. But anyway, then, well, I'll just say some things and leave them hanging. The number of 2 modular simples would be 12. I'll put a little bit of, yeah. B would satisfy conjecture of Winkleman called the gluing conjecture. So these are Semerero. And then I'd like to mention, presumably, K of B, so the number of ordinary irreducible characters in the block, would be a polynomial. I wrote it down here. (155 over 7) n2 to the L.
You can also deduce the Riemann hypothesis.
Really? Oh, that would be great, yeah. Okay, so that's sort of the And I said it would be a leisurely kind of pace, and so now I'll start to move towards stating the theorem. Let's see. This is a result of scenario. Okay, yes, so sol Q subnormal and then involution centralizer. So it's lots of background that so this is part of this work is situated within program of Michael Aschbacher for classifying simple fusion, or a large class of simple fusion systems of component type. So, but it's also seems to be a good way to look for exotic systems at the prime too. So let's. I'll say a bit more about that in a second. But first I wanted to, yes, I never really said, yeah, let me add something to the theorem. Moreover, let's call it F. Yeah, I'll call it sol Q. Moreover, sol Q has one class of involution, or in other words, one isomorphism class of subgroups of order 2 in the category. And the centralizer in sol Q of, say, the central element, central involution in the center, isomorphic to the fusion system of span 7. Okay, yeah, so I probably should have said that. Okay, so, well, that's good that I didn't say it, because I hadn't defined the centralizer of a subgroup. Okay. So, so we have a subgroup of, anyway, to state the theorem, I need some background, and I won't define everything, but I'll just write down the definition of the centralizer of a subgroup in a fusion system. So F is a saturated fusion system over a P group. Yes. Okay, so the centralizer is a subcategory. Objects are the subgroups of now the centralizer and S of R, and morphism are those between the subgroups P and Q, both centralizing R, are morphisms from P to Q in F, with the property that there's an extension to PR of phi, such that phi restricts to the identity on R. So, anyway. That gives us a notion of centralizer. Now, this is a fusion subsystem. It is not in general saturated, but if you take R appropriately in its isomorphism class, then you can arrange that this system is a saturated fusion system. So when I continue to go on, I'll probably ignore this fact completely. So some of the things won't be quite, some of the statements won't be quite right, but I think it'll communicate maybe the flavor a little better. Okay, so let's see, we also have also have well, we have the notion of a normal subsystem. This gives, so therefore we have a notion of a subnormal subsystem. And also can say what a simple system is. Okay, so some examples of normal subsystems are would be the center of F. This is actually a subgroup of S. And but if you view it as a fusion system on itself, then it is a normal subsystem in that regard. We also have the notion of the commutator subsystem. This is a fusion system on the focal subgroup. So once we have those, we can define what we mean by a quasi-simple system. That's a system in which coincides with its commutator subsystem and the quotient. Yes, I did mention quotients, but the quotient by the center is simple. Okay, so if we have quasi-simple and subnormal, we can talk about a component. This is a quasi-simple subnormal subsystem.
Do you need quotients really, or would you say the largest, all proper normal subsystems are in the center?
Let's see, all proper normal, is that equivalent? That's what you're asking? I believe that's equivalent. I don't remember seeing it written down somewhere, but yeah, I believe that's equivalent. Never had to maybe use that property. Okay, so now this is a fracture letter, frac C. Yep. And this should probably have like a bit of an asterisk about it. The collection, so it's a set of components in centralizers in F of, I need to take P equal to 2. Okay, yeah, take P equal to 2. You can look at the collection of components in all components that appear in centralizers of involution. And then, I guess Aschbacher's program in short form is basically the task of solving the following problem given saturated over 2 groups. If F is simple. Yeah, so I probably should tell you what a fusion system of, I should say what a fusion system of component type is. Yeah, Okay, so we may not have any components in centralizer of involutions, and then we're in characteristic 2 type. So let's look at yeah. So definition of component type. See if this collection is not open. Okay, saturated fusion system over a 2 group. If F is simple of component type, and all members, all components and involution centralizers are known quasi-simple fusion systems. Then we want to show that F itself is known. And in this generality, Aschbacher does not propose to solve this problem in this generality. That would be proof of the, say, a classification of all 2 fusion systems of component type. He only proposes to at least look at a subclass to avoid certain difficulties in the original classification. So let me not get into the details. I'll say a bit about that in a second. Yes. So let's see. What are the known quasi-simple fusion systems? Well, let's see. This is how you add all the fusion systems of simple groups. Then you take out FS fusion systems of certain simple groups whose 2 fusion system is in fact solvable. So G has a group of Lie type and Lie rank 1. Or G has a abelian Silo 2 subgroup, so that would include, so we just touch you the groups in J1. Okay, take those out. They have solvable fusion systems, and then add in the Benson-Solomon systems.
Did you want to say quasi-simple?
Probably. Yeah, simple. So I wanted to say simple.
Oh,
And then just say that, you can't make an exotic fusion 2 fusion system by taking a central extension of a group one. So yeah, so this gives you the list. Okay. Okay, so now I think I can state the theorem.
I guess I could say the shared multiplier of sol Q is known as well. The shared multiplier of sol Q is known, as you already said.
Yeah, exactly. So, yeah, you're right. So yeah, now I can take the theorem.
you're saying these are also then no quasi-simple?
I didn't say, I just said they're the, yeah, I mean, I just didn't want to have to write down central extensions for the groups I'm getting rid of if I don't have to. I don't even know. Probably, I didn't check this room. Yeah. What was the question?
I thought from the words you said, these are also the known quasi-simple ones.
No, you have to take you have to, I mean, I could probably said it with not much more work, by writing down all the quasi-simple groups and the ones, G quasi-simple and then exclude. But I'm just saying that, if you take a central extension of, if you have a central extension of a group fusion system, it's realizable. So it comes from a central extension of it comes from a central extension of the original group. So, in that way you get all of the covers of these fusion systems. Okay. So here's a theorem. We have the saturated fusion system over two groups. And we'll want to give it a name, probably. Yeah. Yeah. Okay. Assume all members all components of involution centralizers are known, and some member is isomorphic to the Benson-Solomon system. This is sort of the most general thing you can say, this theorem that I'm stating now. I mean, with the current, yeah. Then there's an involution, T and S, and a component D of F now, out of any involution centralizer, such that one of the following holds. First of all, it could happen that C is already a component in F, and that's a quite degenerate case. I mean, for example, just maybe a cyclic fusion system of a cyclic group of order 2 direct product with swell cube. That would be one very degenerate case, but of course you could have other situations. So C itself is a component of F, and in particular F is not simple.
C is CFT.
C is the component isomorphic to swell cube. So there's a way to take a conjugate by some element of S, at least, and T conjugates D somewhere else. In fact, these now commute with each other, and like usual components, they're not equal. And yeah. What you have really is a direct product, and C is diagonally embedded. In this direct product. So that would be the case if you started out with small q grade cyclic group of order 2, for example. And then 3. Yeah, so, yes, this component is T invariant. It's isomorphic to the next largest Benson-Solomon system, and T induces a field automorphism of order 2. And C is the centralizer in D of T. So in particular, F is not simple. Corollary. If F is almost simple, let me put quotes, simple, then and satisfies the hypotheses, then commutator subsystem is isomorphic to the next largest Benson-Solomon system, and this involution is not in there. So F is not simple. In particular, I mean. But you can't have this, you know, you of course can't have next largest Benson-Solomon system with field automorphism on top. That's fine. So, and I was going to say a bit about how this fits into Aschbacher's program. Actually, I'm definitely behind time. This is the general Benson-Solomon problem, but this doesn't strictly fit into Aschbacher's program. It's not a problem to be solved. It is more than what is needed. And so let me just say to finish, instead of telling you in detail, let me just say that so within Aschbacher's program, so this theorem that I just stated, so the general Benson-Solomon problem, we use the result from the program of Walter's theorem for fusion systems, which very roughly gives the characterization of the Walter's theorem for fusion systems, which naturally is due to Aschbacher, and gives a characterization of the fusion systems of groups of Lie type and odd characteristic, according to, so the theorem says that, I was going to state it, but I'll just say it aloud. So it says that if you have a simple, well, a special case is, you have a simple saturated 2 fusion system, and some member of some component in the involution centralizer is the 2 fusion system of a quasi-simple group of Lie type and odd characteristic, and not too small, then F itself is a 2 fusion system of a group of Lie type and odd characteristic, or it is a Benson-Solomon system. So this is used in order to prove this general theorem but a special case called the, it's proved by us with the, with the right hypotheses to fit into the program, and that's one of the ingredients in the proof of Walter's theorem. So we proved a special case within the context of the program, and then we deduced the general form from Walter's theorem. And that's all I have time for. Thank you very much.
Thank you very much. Questions, remarks?
So what's the status of the Aschbacher program? Finished or just started?
So I think in AKO, Walter's theorem was somewhat step 3 of 4. And in the sense that after Walter's theorem, you have only finitely many involution centralizer problems to solve now. And so after this theorem, it's reduced to, as far as I know, a finite number of cases. Roughly 20. Is it breakfast time in Pasadena?
Is it expected that that's the full list of simple tube fusion systems? Or?
It's looking like it. Yeah, it's looking like it. Although there are a number of small pesky involution centralizer problems that were typically quite difficult that still need to be done, like well, I don't know if I'm going to maximize the difficulty and give you something that's, I don't know, but yeah, so who knows, but yeah, it looks pretty bleak for a new exotic fusion system, at least rising out of this, at least for fusion systems of so-called odd type that he's wants to classify.
Is anyone trying to find exotic fusion systems on groups of order 2 to the 10 then?
Oh, I think there's somebody in this room.
Chris and I are working on that.
Yeah, they have computer code now.
We're
That's,
gonna use it, yeah. So what about the characteristic P-type case, the characteristic 2-type case?
characteristic 2 type.
Yeah.
Yeah, that's it's. As far as I know, it's quite uncertain. There's if your goal is to take this the classification of fusion systems and then give, which is I think it's most people's goal, to give a new proof of the classification of finite simple groups, and the question is, do you want to do the characteristic 2 type within the category of fusion systems, or do you want to return to the category of groups where, I don't know,
Okay, if there are no further questions, let's